Valve does nothing and wins, Valve does something and wins even more. Maybe you've heard about Valve developer Natalie Vock working on some Linux patches to improve the Linux gaming experience with low VRAM GPUs. And by low, we mean less than 8 gigabytes, which is a crazy number to call low. But that is the way that things are going. There's been some coverage on places like Phoronix and Tom's Hardware and various other places. However, we also have a blog post directly from the developer fixing AMD GPU's VRAM management for low-end GPUs. Whilst the initial focus here was with AMD GPUs, there are additional patches for Intel GPUs and also for the Nouveau drivers, the open source drivers for NVIDIA. The proprietary drivers, as is often the case with any improvements that happen on Linux, they're not for the proprietary drivers. Also, whilst the main focus here is going to be on low VRAM GPUs, because not just generating VRAM out of nowhere, it is more efficiently and more effectively using it, so having less VRAM, that's going to have a greater effect. If you have a, 12 gigabyte card and you're maybe running mods with crazy high resolution textures and things like that, this is still going to affect those cards, just not as much. It may sound unbelievable to some, but not everyone has a data center beast with 128 gigabytes of VRAM shoved into their desktop PCs. I don't actually want a data center card because that'd probably run really badly for gaming. However, if you want to give me 128 gigabytes of RAM, that would be nice. I'm not going to use it. I'm going to sell it and probably buy a car, but I'd still like it. Around the world, people tell the tale of a particularly fierce group of Linux gamers, those who dare attempt to play games with only 8 gigabytes of VRAM or even less. Truly, it takes exceedingly strong resilience and determination to face the stutters and slowdowns bound to occur when the system starts running low on free VRAM. Carnage erupts inside the kernel driver as every application fights for as much GPU memory as it can hold on to. Any game caught up in this battle for resources will surely not leave unscathed. That is, until now, because I fixed it. Now, if you don't care about any of the technical details, all you care about is, I want, maybe, depending on the games you play and the card you have, more performance. What do? You will need some kernel patches and some additional utilities to make use of the kernel capabilities properly. The simplest option? Use CacheOS, specifically with KDE as your desktop. There is no reason this couldn't be done with something else. The functionality for these patches, though, relies on some additional things built into KDE. On CacheOS, with the kernel version 7.0 RC7-2 and up, so very, very recent kernel, and the user space utilities are available in the package repositories. All you need to do is use CacheOS with that kernel version and install dmem cg-booster and plasma-foreground-booster, and you should be good to go. What about on something else Arch-based? Right now, this is still very early days, so eventually this is probably going to be something just built directly into SteamOS, but if you're on something like, regular Arch Linux, for those, you need to go and install the packages, so dmem cg-booster and plasma-foreground-booster. Both of these are in the AUR, with plasma-foreground-booster dmem cg being the package name. And then on the kernel side, either install the CacheOS kernel, which is something you can do. I don't personally run it myself. I know some people are a fan. If you don't want to do that, there is a custom patched kernel available in the AUR, Linux-dmem cg. Go and use this, or if you're comfortable doing so, you can apply the patches yourself to the kernel. Those are your options. I would recommend just install the CacheOS kernel, then you get some additional CacheOS improvements as well. But right now, we're still very much waiting for things to be properly upstreamed. If you're not on something Arch-based, now you got a bit more work to do. You pretty much are going to have to patch it yourself, or you can go and package up the CacheOS kernel. If you're on anything else that is not Arch-based, you're best off just waiting. Let alone the fact the other utilities, the dmem cg booster and plasma foreground booster, are not, to my knowledge, packaged anywhere else. You're going to have to go and compile those yourself as well. And if this is not something you're comfortable doing, just wait. Or switch distros. I kinda lied when I said you had to use KDE. There is another way you can go about it, and that is using a newer version of GameScope. This is the Valve compositor. This is what all the games are run in. When you run them on the Steam Deck, when you run them on the upcoming Steam machine, you can just use this on any distro as well, and this lets you deal with a lot of problems that games have with resizing and various other things, in which case you still need to install the DMEM-CG booster. Also, you will still need those kernel patches, so make sure you're on a distro that has the kernel. Another thing is you technically need systemd. All the user space utilities hard depend on systemd. Without systemd, you need to write your own utilities that make use of my kernel patches. Something needs to manage cgroups in your system, and that something needs to enable the right cgroup controllers and set the right limits. What that means, we'll get into in the technical section. Basically, you're going to have to be on something that has systemd, which is most distros, but if you're on something like Devuan or various other things like that, it's going to require quite a bit more work. With that preamble out of the way, what are the changes actually doing? As I said, it is not generating VRAM just out of nowhere. On a standard desktop system, something where you have a window manager or a desktop environment installed, the game's not going to be the only thing that is accessing the GPU. You're going to have the desktop itself. It's going to be rendering panels and widgets, and maybe you have a browser open, and the browser is using some of your GPU, and then you have multiple browsers open because you have web apps open, like Discord, and you have various other applications running on your system, all of which want to use the GPU, and all of which are using some amount of VRAM. Now, you can get around this. You can run a kiosk-style system and only have the game open and no actual desktop. It is just the game window, and that is the only thing being rendered. Most people are just not gonna do that though. To properly stress test kernel memory management when working on this issue, I would go ahead and open up nearly every app with an integrated browser engine that I had installed. Viewed in AMD GPU top, the result of that looks something like this. If I go and run that on my system, AMD GPU underscore top, we are using about 1 gigabyte-ish of VRAM. There is also this GTT here, and we'll get to that. On this system, with all of these things running, about a quarter of the VRAM was being used. Now you open up a game like Cyberpunk 2077, and, well, you don't really have a ton to spare. But something weird is happening here. So GameThread is the game. It's using a lot of VRAM, but it's also using a lot of GTT. This is memory accessible by the GPU, but physically located in system RAM. Think of it like swap for your GPU. So GPU, when it goes to swap, it goes to your system memory goes to swap, it goes to your drive. And of course, not to the same extent as accessing a drive, especially a mechanical hard drive, system memory is slower than VRAM, so when it goes to GTT, things will be slower. Technically, most of the time, but not always. Some amount of memory landing in GTT is normal. Many games will intentionally allocate memory in GTT because it is advantageous for some use cases. However, Cyberpunk 2077 allocates a fixed amount around 650 megabytes of GTT. That is required. It will go in GTT. Anything more than that is basically the game not being able to get the memory it wants to. In this case, about an extra 720 megabytes that should be, if there is VRAM available, in the VRAM. In kernel land, this process is referred to as eviction. The system in total tried to use more VRAM than there was available at all, so something had to give. Instead of telling the app that memory allocation failed, which would mean a near certain application crash, the kernel decides to kick some memory out of VRAM to make everything fit. This degrades performance, but at least it allows every app to continue running. Nice. If only it would evict literally anything other than the game, which is the very thing that suffers the most from having its memory evicted. Why in the world would it decide on that? Very simply, because Linux doesn't discriminate in what wants VRAM between games and non-games. To the kernel, everything is just something requesting memory. If it wants the memory, it can usually just have the memory. And to a general purpose system like the Linux kernel, something that was not made specifically for gaming, that makes sense. That is the best way to handle things. You can't just decide, oh, I think this is more important or that is more important. Any decision you make is going to break some use case, so best choice? Don't make a decision. In the beginning, things worked rather simplistically. If applications wanted VRAM allocations, the user mode driver would go to the kernel mode driver and request VRAM memory. Save for some exceptional cases, that request would be granted, and that memory would be kept in VRAM. If another application requested VRAM allocations and the memory was kicked out, the kernel driver would move the memory back into VRAM the next time work was submitted to the GPU using that memory. So work would go in, work would come out, work would go in here, and then basically, this is not intentional, but it works really well. Memory would bounce back and forth, and the work would get completed. The problem is that leads to a lot of movement of that memory. All this moving ended up with worse performance than if the memory had never moved in the first place. The first band-aid solution was to rate limit memory movement inside the kernel. Once the kernel driver moved enough memory within a specific time frame to trigger a limit, no more memory would be moved for some more time. This indeed reduced moves, but didn't do anything to fix the underlying issues of repeated cyclic memory movements. Worse yet, repeatedly running into this rate limit would introduce annoying jitters and stutters as the kernel driver rapidly alternated between moving memory and doing nothing. If you hit a period where you needed the memory, and then the memory could not be moved in, well, you just have to wait until the memory can be moved in, and then it works. And that isn't going to be something where it's like multiple seconds in most cases, but it is something where a user is going to notice, hey, I just lost like 50 frames for no reason. Eventually, to combat the still existing overhead of repeatedly moving memory, user mode drivers changed their allocation strategy. Instead of specifying VRAM as the only acceptable domain to place the allocation in, every VRAM allocation request would specify both VRAM and GTT as possible memory domains. The kernel would interpret this as VRAM being preferred, but if there was no space, GTT was an acceptable fallback, and the kernel wouldn't try to kick out other VRAM memory to make space. This is a much better solution, it's a much less stuttery solution, but it's still not a perfect solution, because when you have VRAM intensive applications that are very time sensitive, like real-time games generating 60 or 120 frames per second, going to system memory is still not preferred. The preferred thing to do is always stay in VRAM, if at all possible. There is no single right decision to make here. Being aggressive is wrong, and not being aggressive is wrong too. To be more specific, they're wrong in different cases. It makes complete sense for a game to be aggressive, but it makes no sense for random background apps to be equally aggressive. Random background apps should not be aggressive at all, but if the game backs off equally quickly, that doesn't help much either. However, not every single background app should be completely unaggressive. Something like OBS, you want it to have the VRAM that it wants to have because you're trying to capture the screen. The reason why it's open is specifically for that function. And there are various things you might be running, like a game overlay or other things that you want to be running in the background that should also get the VRAM they want. The real problem is that to the kernel driver, all memory looks the same. The kernel doesn't know if it's dealing with a highly important object from a game or a static image from a web page running in the background. All it sees is a list of buffers. As long as all buffers look the same, it is impossible to have the same approach work well for every one of the widely different situations a driver may encounter. However, there's a way to deal with that. Give it some information to work on to know what each of the memory allocations is trying to do. For that, we have cgroups. They're super great at organizing random batches of processes into single organizational pieces. If you make a compile job C group and put the make process in it, all compiler processes it spawns will be part of that C group too. Don't want a big build hogging up all your RAM? Set a limit with a C group memory controller. Want to have some CPU time for some other things? Just set a CPU limit with a C group CPU controller. It's great. You can have C group hierarchies too, and represent almost any kind of complex resource distribution you want. Luckily, systemd agrees that C groups are cool. Every systemd unit is actually represented with its own C group, and as it happens, desktop environments will represent each desktop app as a systemd unit. How convenient. Complex resource distribution sounds exactly like the problems we're having in GPU land if only someone wrote a C group controller operating on memory allocations from arbitrary devices such as GPUs. That's what was done. With the DMEM C group controller, the kernel now learns about memory protection. Memory being protected merely means the kernel will go to significant lengths to avoid evicting that memory. For example, it may try to find memory from a different C group that is not protected and evict that instead. C groups are all about resource partitioning, so for a C group you can assign a protection limit. That is, if a C group's memory usage is below that limit, its memory is protected. As soon as it exceeds that limit, the memory ceases to be protected and can more easily be evicted. Now the DMEM C group controller, this had been upstreamed for quite a while now, but for it to work properly in the context of gaming, you will need these additional patches. The thing that is really cool about this is it's not just something decided on by this developer and you just have to accept whatever they decide. This is completely dynamic and controllable in user space by you, the viewer. Window managers can now determine whichever app is in the foreground and dedicate the highest priority to that app via its C group, completely without having to teach the GPU driver what a window or foreground is. For desktops, this is an important heuristic, but it's totally not the kernel's business to know the concept of a foreground app. I personally use KDE Plasma as my desktop environment, so when looking for how such a thing could be integrated into Plasma, lo and behold, it was already done. At least for your regular system memory, not for the VRAM. This prioritization work was also done via C groups, so adding VRAM prioritization in my fork was pretty much a walk in the park. Except for one thing. The foreground boost utility doesn't manage C groups and C group properties directly. systemd is responsible for managing C groups, so foreground boost just communicates with systemd to set the C group properties. That's not too bad though. Let's just implement support for the DMEM group controller in systemd, right? Well, this is what I thought too, but as I alluded to before, fixing VRAM management for gaming purposes is by far not the only purpose of DMEM C groups. There are quite a few other use cases that people are eyeing DMEM C groups for, and if I were to implement a systemd interface while only considering the gaming scenario, the other use cases run the risk of having to deal with a systemd interface that wasn't designed with that use case in mind at all. So for now, a common systemd implementation seems mostly off limits until the dust has settled some more. So instead of doing it through systemd directly, kinda just, do it behind their back. This is the final piece of the puzzle, DMEM CG Booster, and it does it safely and blazingly fast, in case you couldn't tell. Rust. After systemd constructs the C group hierarchy, DMEM CG Booster goes over those C groups and additionally enables the DMEM controller on them, in order to activate the kernel functionality that ultimately allows for GPU memory protection on those C groups. While at it, it also sets some settings in the C group hierarchy that allows the memory protection to kick in properly. This is a kind of messy and not great stopgap. Once systemd gains proper support, you'd express all of this with drop-in unit configurations, which is much prettier. The DMEM CG Booster utility is exclusively there until that proper support happens. And with all of this work done, now we have Cyberpunk 2077. Obviously, most of the VRAM is still being used because you're still running Cyberpunk. However, the only memory for Cyberpunk in GTT is 650 megabytes, the part that is explicitly allocated to system memory. Everything else is just fitting in the VRAM. Everything else is just eating away at whatever might be running in the background and just giving it to the game. Now, this does mean it leads to slightly higher system memory usage when running a game. But that is preferred over higher VRAM usage. Instead of performance slowly degrading over time, games should perform much more stable, as long as the game itself doesn't use more VRAM than you actually have. Generally, it seems like even modern games stay within a memory budget of around about 8 gigabytes. That is until you start going to like ultra settings, things like that. So if you have a GPU with 8 gigabytes of VRAM, you should be good with today's games. Now, tomorrow's games, well, we'll see about that. And even, to be fair, some of today's games on the higher settings, there's a good reason why a lot of people are not happy when a card comes out that has 8 gigabytes of VRAM, because game developers are really stretching that VRAM limit. As I said earlier, this does work with Intel GPUs as well, and theoretically, this should all be good. It has not yet been tested. Also, there is a separate patch for the Nouveau drivers for NVIDIA, so hopefully, you could obviously apply the patch yourself. Hopefully that does get upstreamed. As for proprietary NVIDIA, good luck. Now, for iGPUs or AGPU systems, will these benefit? It's unclear, because they use the system memory as VRAM generally. Maybe it has some benefit, but it's already using system memory as its VRAM, so probably not. Someone should test that though. Whilst I do have a 12 gigabyte card, this is something that would still affect me on my system. I'm not running KDE right now. I do have it installed though, so assuming other environments don't get something to sort of bridge that gap and easily configure it, I might have to just game on KDE when this gets upstreamed. I don't know. All I know is it's another Valve W, another KDE W, and that's good in my books. So, let me know your thoughts down below. Again, one more thing. There's no reason why it couldn't be done on GNOME. If somebody wants to do it on GNOME, they probably could. But the tooling is just built for KDE right now. Anyway, if you like the video, go like the video. Go subscribe. Yeah, like the video. Yeah, do those things. If you really like the video and you want to become one of these amazing people over here, check out the Patreon, Scribe, Stelly, Bearpay, linked in the description down below. That's going to be it for me, and more gaming.
Like this.